Okay, first, please download this IV102 and IV-10 examples, and also the menu, IV for Grasshopper menu 10. Okay, the first one, IV102, is to install the plugin for Grasshopper. And IV is a package for creating mesh graph. Graph is a kind of mathematical construction, very, very useful mathematical construction. It is very important for computer algorithm. And for the algorithm for unrolling a mesh object, we need to use graph to do the analysis. And today I'm going to explain to you the basic concept of graph and how is graph related to the unrolling of mesh objects. Okay, and then we are going to use these examples. They are Grasshopper examples which show us how to use IV to control the unrolling of a mesh object. And this one, IV for Grasshopper menu, is explaining the component provided in IV. So if you install IV in Grasshopper, then you see this group of components here. Okay, it is in order to use it, we need to learn about graph. Okay, otherwise it will be very difficult for you to understand how it works. Okay, first let me show you the first example file. We start with a mesh. No, we try a simpler one, which is this one. This is a mesh. And we want to make a model of it. And of course, the straightforward way of making it is simply to dissect it based on the mesh edges. For example, this mesh is a triangulated mesh, so it consists of a lot of triangles. So we can use laser cutting machine to cut these triangles and then glue them together. But if we do that, there will be a lot of unnecessary cut, right? Because if we are able to fold, then we don't need to cut all the edges. Maybe we just need to cut a part of the edges. And then we can use like a CNC or laser cutting machine to cut the planar material. And then we fold on this line, either mountain fold or valley fold. And then we need to glue only the part that we are unable to unroll without overlapping. Because if you unroll all the triangles, and this is not a planar mesh, so some part of them might be overlapping. And in that case, it is impossible for you to cut this part in a planar sheet of material. So we have to dissect them into parts. And then we can rearrange these parts so that the surfaces are no longer overlapping after they are unrolled. Okay, and then when we want to make this model back into 3D space, then we need to glue the edges that have been cut when we try to rearrange it. Okay, so this is the whole process. But then we need an algorithm to dissect this mesh into part and then unroll this part, which means to unfold the surfaces so that they become entirely planar. Okay, so this is the mesh. Okay, and using Ivy, we need to convert this mesh into a graph mesh. Okay, what is a graph mesh? Here, with this component, we can show it. Simple enhanced periodic distance show not row extra node. Okay, so if you take a look at this, before we convert it into graph, it looked like this, right? So it's a triangulated mesh with a lot of triangles. And then using this component, we derive a graph. And here we can show both the derived graph Can I show the, okay. Both the derived graph, which is in cyan, with this little square, the squares are the node of the graph, and the edges are the connection between nodes. So from here you can see that the relation, you can see the relation between the base graph, which is shown by this darker straight line edges here. Okay, this is a surface, this is a face of the base graph, and this is another base graph. Base mesh, sorry. One triangle, one face of the base mesh, and the neighbor face of the base mesh. Okay, and this triangle, the center of this triangle is marked with a square, which represents a node in the graph. Okay, and this node represents the entire face. And the other face is represented by this node. And then the two nodes are connected if the two faces have a shared edge. Okay, and this edge simply follows the two faces and then connecting the two nodes together. Okay, so the function of this component is to create this graph, or you can call it a network, okay, shown in these cyan lines and squares. Okay, so you can think of this graph is like a network representing the connectivity of faces in the mesh. Okay, for example, this face is adjacent to this face. So the two nodes representing these two faces, they have a connection. Okay, this polyline connecting the two nodes. Okay, so the entire mesh is shown together with its, they call it mesh graph. Okay. So based on this mathematical structure, we can go on. We can assign weight to all the connections, and this weight can be depending on your preference of dissecting this mesh. Okay. you can have different way to assign weight. And then there's another component which use an algorithm to find the gross spanning tree of this graph. Okay, you see, now it is a network. And a network can have loops. For example, this is a loop. If you follow the cursor, then you see this is a loop and this is another loop. Okay, and then this algorithm is to find a tree or trees that can cover all the nodes, but without preventing any curve. So if we convert it into trees, then you see there is no loop, right? You take a look at the cyan edges. The thickness is shown here. Let me see. Okay. Weight enhance normal preview. Okay. Now all the edges are thin lines. So you see, there is no loop, but still all nodes are included. And this network, without any loop, we can call it a tree. Okay, because here you have a link here, and then you have two branches split into two branches. And if you follow this branch, then you go on, and here it is split into two branches again. And you follow this one, you go back to the joint, follow the branch, and then go back to the previous joint, and then follow the other branch. So you can go on like this until you traverse all the nodes. So this is a tree, and this tree has a specific relation to the previously this one. This one has loops, but this one don't have loop, but they have the same set of nodes. Okay, so we call this a tree in the network. Okay, by removing some edges. Okay. So this tree is important for the algorithm that unrolls a mesh object. Okay. I simply go through the process, and then later I will explain the detail. So after we derive the tree, then we can go on and we try to unroll it. So far you are not able to see it, but then we need to do some geometric transformation so that we are able to locate all the figures into the right position. And if we take a look, then you see this. They are too much because some pieces are all repeated. Actually, I think here we need to only 2 rows and 4, 5 columns. Okay, and maybe we need to separate them a little bit. Okay, so the entire mesh, now it is dissected into 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These 2 are redundant because it simply repeats the last 2. Okay. Okay, and they are all planar. So if we turn it, you see they are all on the XY plane. And this line shows the folding edge, okay, and the boundary is the cutting edge. So we can use a laser cutting machine to cut the shape, and these are flippers for glue to connecting another piece together. Okay, it is optional, so we can cut it with these flippers or without. Okay, so eventually the whole mesh we can fabricate it by cutting these 10 pieces and then fold it based on the angle which is required, and then glue these pieces together, then we can produce this mesh. Get it? And then you can create your own mesh, and then this program, this process, you follow this process, it will create all the shape which is required to cut. Okay. Victor, have you been using Ivy? No? And before, how did you do things like this? You haven't done this? Okay. Okay. It is not so complicated if you understand the process. Okay. And we can try a more complicated shape. Here, the example shows here. They have another mesh. Which is this one. Okay. And we simply, first we triangulate it. Okay, this is a C# program which try to weld vertices, but I think it is not necessary because here we don't find any overlapping vertices. Okay, so after we put this as an input, and because now it creates more pieces, so we have to change some parameter. First, we can check how many pieces. Unrolled mesh. 109 pieces, which is needed. So we have to rearrange it. Before we have only 2 rows and 6 columns. Now, let me disable it. Now maybe we need 10 rows and 11 columns. Enable. I'm not sure if the offset distance is enough, but then we can take a look at it. Okay, and I think the last 2 are identical. Okay, so this one is not necessary. So these are all the. I mean, you can consider this as shop drawing. Okay, and it is marked with some ID number, and we can adjust like the distance until some of them overlap. Okay, or you can bake it and then rearrange it so that you don't waste any material. And the text size, the size of the text, we can adjust another parameter, which is this one. So now maybe they are too large, so we make it smaller. Okay, until you think it is okay. Okay, and this is the flipper. The flipper seems too large, so we can adjust another parameter. Where is it? Here. Width, we make it smaller. Okay, and this beaver will decide the angle of it. Okay, you can have sharper or not so sharp. Okay, but when it is not so sharp, then sometimes it might be overlapping with the flipper next to it. Okay, so you simply have to decide. Okay. Okay, sometimes if the angle here is too sharp, then these two flippers may overlap with each other. Okay, so I want you to know what is the purpose of going through the whole process. Okay, and then with these drawings, we can use laser cutting machine to cut it and then to fold it if it's metal or whatever material, fold it and then we glue it on these flippers, then we can create the object. Okay, any questions? So this example shows the overall process. But then the following examples shows you how to do it step by step. And along the way, I need to explain to you what is graph and why graph is so much important when we want to implement a process for unrolling the mesh object. Okay. Questions? You never ask questions. Why? You don't have any questions? No? Really? Okay, so please download IV102 and install. Sorry? Yeah.
So it will arrange is like one row, two row, because there are so many separate components. If I print it out, how do I connect them? Where should I align?
Okay, so that's the reason why they need to put this text. When you look at the shop drawing, you see there are, right? You see? Okay, so you have to match. Okay, like this one is 10293. And I think you will figure it out. Okay? This surface, this triangle is 3737. Okay? And this edge is 10293. Or maybe it has to be, okay, this flipper has to connect it to 10293. This is a surface, a face. You see this piece, the entire piece, all triangles start with 3, right? 3288, 3736, 3289. So for this part, we have to find piece number 10, okay? And then in piece number 10, you'll be able to find 292, which is a face. And this has to be connected to that face. Okay, so let's try to find 10292. This is 3, so where is 10? This is 25. Wow, not so easy. 13. What is this? 11. Okay, so 10 should be 10 should be here, right? Sorry, I don't remember which number is that. But anyway, you'll be able to find it, right? So if it is 10, 300, then it should be this edge, okay? And if there are more than one edge, then I think you can compare the length of it. Okay. I guess the way they do it, maybe you never oh yeah, here, yes, you have two edges. Okay, okay, it's okay, because on this side it also shows that this edge is without clippers, right? Because you only need one. Okay, there's also an option so that you can have both. Okay, but I just chose to have one clipper. So you just, this edge is connecting to 9299. Okay, so I think the mark is very clear. You just need to find out where is which. Okay, questions? So if you unzip the file, let me see. If you unzip IV examples, okay, this one is for the plugin. So you copy these two, okay, copy these two files. And before you unzip this file, make sure that you uncheck the block. Okay, here I have already done it. And after this, you unzip it, and then it creates these two files, IV and IV script.dll, and copy this file to the component library. Okay, and you'll be done. And these are the set of examples. The one I just showed you is the first one. This one is kind of the overview of the entire process. And then the example from the second one shows you step by step. Okay, what are steps? Okay, and why we need to do that. Okay, and the last ones, there are some additional decoration. For example, you want to cut holes in each faces. Okay, and you also want to include this part into your shop drawing, so it is necessary for that. Okay. So.
One question.
Yeah.
Is it important to find the mountain fold or the valley fold? Because if you have a material that is have a certain thickness, you need to cut.
Yes.
So it's easier to fold.
Yes. When you show this shop drawing, you'll be able to put this line into different layers or different colors. Here, which is here, you see. No, not here. I have to select it. Okay, so these are the cutting edges. So you can use this preview. You see, custom preview. Okay, and you assign a different color for that. Okay, for the cutting edge. And I think this is either the mountain or the valley fold. Okay, and this is the other one. Okay, so you can have three colors. Okay, one for the cutting edges, one for mountain fold, and one for valley fold. Okay, and when you use laser cut to cut, maybe you have a dot lines for the valley fold. Okay, and you have dash lines for the mountain fold. Okay, and then you have how do you call that? The more intensive laser to cut the edges, and also you have the text in a different. I mean, anyway, you just find some way to show them. Okay, maybe very light laser to simply mark on the material that you are doing. Okay. Okay, so let's go to the second example. Here we start with this mesh. this is not a planar mesh. First, I want you to think, how can we unroll it? How can we unroll it? If we have two faces, okay? The angle is theta. And then we use the first face, the first surface as the face. And then we have to rotate the other face using this edge, this shared edge as the pivot, right? And then we do the geometric transformation to rotate it on this axis with this angle, right? But how about if we have another face? And maybe another. Okay, how can we do that? We cannot do it all at once, right? So we have to choose one face as the initial face. Okay, for example, we choose this one. We mark it 0. And then for the rest of it, now we have to treat the rest of them as one part and rotate all three faces together using this edge as the pivot and then rotate it. So we first unroll these two faces first. So after we do that, then maybe we get something like this. Okay, and then okay, get it? You can use a piece of paper, then you try to unroll it, then you understand it, right? Long strip of paper, and then you fold it many times, whatever you like. You start from the first face, and then unroll the second face, so that you make the first face planar with the second face. And then all the rest simply follow this action of unrolling. And after we have unrolled the first face and the second face, then we can ignore the edge between the first and second. And we do the same thing for this entire face, and then unroll this face and this face. Okay, and after the second step, we get one more surface planar to the previous ones. Okay, and we go on until we unroll all faces. And then the condition is that this is one linear linkage. It's in a sequence. How about if it has branches? If you How about if it is like this? This is the first face, and then we use this edge as the pivot. And imagine that if there's a folding angle, then we unroll this surface together with all the three other faces. And then this is the next one. And then we can choose any of the three, right? So maybe we choose this one as the next one, and unroll this one, okay, flatten this one, and then maybe this face. So it's like traversing through all the faces. You need to decide a sequence of it. So if we connect all these nodes, then we get something like this. Okay? And there's an order of all the nodes for the traversing. First, we take this one, and then we go follow the edge here, And then follow the edge here, because it is a dead end, so we don't need to do anything afterward. So we go back to the previous node. And then find if there are some other branches where we haven't visited yet. So, okay, this one we haven't visited. So we go to this one and flatten this face. And then there's no more branches. So we move back, and then there's yet another one to be flattened. Okay, so this is called a way to traverse a tree. Okay, and if there is something more, okay, whatever, we can go on. So when we flatten this part, all the rest will go together with this one, right? And then we can go on after we have done this one. We go on for this one and the 6, and then there are 2 options. You simply choose one of them, 7 and 8. Okay, so the entire mesh will be unrolled step by step, following the sequence, following the way we traverse all the faces. Okay, now I want you to think about the red figure. We can consider this as a kind of network. Okay, or I want you to be familiar with this term. It's called graph, not graphics. Okay, graph. Graph is a mathematical construction which consists of nodes and edges. Okay, all the vertices, they are nodes, and the edges are the line connecting nodes. So if you look at these red nodes and the lines, it is a graph, right? So far, we are thinking it as a mesh. We want to build this mesh back into its 3-dimensional shape. Okay, and when we unroll it or when we unfold it, it becomes like this. Okay, and if we can represent the shape as a graph, the red one, okay, but then this red graph has a dual graph. If we consider this enclosed area as a kind of object, and then you simply find any point, okay, usually we use the center location as a node for the black graph. And then we connect all the nodes. When there is a shared edge between the 2 surfaces, then we connect this node with this node. Okay? There is a shared edges, then we connect this node with the node. Okay, so the black one is a dual graph to the red one. And it is also true the opposite way. So we can also thinking that the red one is the dual of the black one. Okay, so in order to figure out how to unfold the mesh object, we need to convert the graph to find the dual graph of the red one, and then figure out the process for unfolding the entire structure by traversing the node. Okay? And this is not the only order, the only sequence that we can follow. In fact, we can start with any node we like. Okay? We can start with number 4, right? So from 4, we have 2 choices, either going to 1 or going to 5. And we just need to choose one. For example, we choose 1. So if I write down the order for traversing, then I start from 4, right? And then if I choose the next one, so I get 1. And then after I visit 1, I have 3 choices, 0 to 3. Okay, if I choose 0, and there's no way to go on, so I put it, move back. Okay, this is called depth first traversing. You always try to go as far as possible until you get into a dead end. So now we have 2 and 3. Okay, so you choose one, either one. If we choose 2, okay, and this is a dead end again, so 3 is the only way. So we have finished 0, 2, and 3. So there is no more branches that hasn't been traversed for node 1. Okay, so we finish this branch. Now we go back to 4. And 4 has another branch that hasn't been visited, which is 5. So we go to 5. Okay, and there's only one connecting node, which is 6, so you don't have to choose. And now you have 7 and 8 optional, so we choose 7, and finally 8. Okay, after we complete 8, there's no more node to be visited. Okay, so this is the unroll sequence. First, you find out the angle between, rotational angle between 4 and 1, and then you unroll the part which is connected to 1 using this edge as the pivot. Okay, and then now you have flattened 4 and 1, right? Now you go to this one and then use this edge as the pivot and then unfold 0. After you have done this, 4, 1, 0 become one planar surface. And then you go on, and then eventually you have all the 8 surfaces in a plane, on a plane. Okay? Okay. But we haven't finished the thing yet. Imagine that you have a cube. How many ways to unfold it? Usually, to me, I'm most familiar with this one. Right? But this is not the only way. Okay. Because if we want to draw the dual graph of it, okay, this is face number 0, and 1, 2, and then the one on the back is 3, and then here on the back is 4, like a dice, right? Oh no, the dice is 1, 2, 3, 4, 5. Okay, so if it is like this, so when we start from 0, so 0 is connecting to 1 and to 3, also to 4, and also to 5. No, not to 5, to 2. Sorry. Okay, and 2 is connecting to 5, right? So 5 is here. And 3, 4, and 1, they are also connecting to 5, right? And then 1 is connecting to 4, and wow. 4 is connecting to 3, 3 is connecting to 2, and 2 is connecting to 1. Okay, I don't know, maybe I made mistakes, okay? But you see, there are many different ways to traverse it. Okay. But when we traverse this graph, we'll visit all nodes, but not necessarily every edge, right? We just need to make sure that we visit all nodes. But it's okay if there are some edges that we have not been going through. Okay. And the edges that haven't been going through are the edges that needed to be cut. Right? Get it? So when we visit this node, this network or this graph, if we mark the traversing, what is the condition that we need to comply with? You never have loops, right? If you unroll it one face after the other, what happens if you have loop? We don't know what to do, right? So you see, if we unfold this cube into a subtoroid like this, then maybe this is a 0, and this is 1, 2, 3, 4, 5. And this is the graph, the dual graph. Okay, but in 3D, you see, there is a edge connecting 1 to 2, right? And also 1 to 4, and 4 to 3, and 2 to 3. And also 1 to 5, 3 to 5, 2 to 5. Okay? But when we unfold this cube into this cross shape, actually we keep only the edges that is inside this cross figure. But for all the edges which go outside of this figure, we are not using it. So they are the edges that has to be cut. So you see, these are the edges that need to be cut. You see, from 2 to 5, actually from 2 to 5, I should draw this way. I should draw it this way, because this is the edge that should be connected to 5, right? So this link should go out through this edge, and then connecting to 5 through this edge. And 2 to 3, this is the way, because this edge is going to be aligned with this edge when we fold it into this cube. And this edge is going to be aligned with this edge, so this graph edge is connecting from 2 to 1 through the 2 edges, and also 1 and 4. Okay, and 1 and 5, I shouldn't have drawn this way. I should have drawn this way, right? Because no, sorry. Sorry, here, right? This edge is going to be aligned with this edge. Okay? And remember, one of you just asked about the gluing. So if we have a flipper here, then we simply follow this edge. We know that this flipper has to be glued to here. Okay? And if we have a flipper here, then this part is going to be glued here. Okay? So using this graph representation, it's very clear how we unfold a 3-dimensional mesh object. and dissect into parts. And then also we know which are the edges that need to be brought together to make the object. Okay. A welded two manifold unified normal mesh as the input. Unified normal, which means all the faces are facing to one side. I mean, you don't mess up the normal vectors. Okay. And then we can use this component. This component is in IV. Here, graph from mesh. So we use this mesh to create the dual graph of it. Okay, it is difficult to see, but we can show it so that it is easier to look at. This is the graph. You follow these green lines, and this is the mesh. Okay, but together it's difficult to visualize. Maybe let me preview it. Okay, and if you click the right mouse button, you have some options to visualize it. So we can simple enhance the preview. Okay, so the mesh are shown in this dark and with red edges as the edge for each surfaces, each face. And on each face, there is a node for the dual graph, which is represented with this small square. And then the edge connecting one node, one face to the other is represented with this cyan edge. Okay, usually for simply a mathematical definition, the geometry of this connecting line is not important. Okay, you can connect it any way you like. You can bend it, you can use a curve, you can use whatever, but usually you simply use a straight line segment. But in this case, because the geometry is important, so the IV, they use this polyline, which is a curve on the two surfaces. Okay, so it is a polyline. Okay, to connect them. Okay, so using this graph from mesh, we get the dual graph. Okay, sorry, I should turn it off.